Alright everyone, let's talk about polyprotic acids. This is video 4.3.2. Polyprotic acids are just acids with more than one proton to come off. And so we are going to look at phosphoric acid. It has three separate Ks, three separate Kas. So Ka1 is for the first proton to come off, Ka2 is for the second proton to come off, and then Ka3 is for the third proton to come off. Okay, so we're starting with a 0.1 molar H3PO4, that's phosphoric acid solution. We're going to find the pH and the concentration of all these things. So, just like before, the first thing that we're going to do is write an equation. So we have H3PO4, phosphoric acid, is a weak acid, so it's in equilibrium, dissociates into H+, plus, if we lost one of those hydrogens, we're only left with two. So we have H2PO4 minus, because we lost an H+. So initial change ending. We started with 0.100, and then of course we didn't have any products yet. Minus x, plus x, plus x there. 0.100 minus x for the end, x there, and x there. Okay, and so now that we have our ice table, the next thing we need to do is write our equilibrium expression, right? So we have to write our Ka, use our Ka expression. So Ka equals products over reactants. My products here are H plus and H2PO4 minus. A reactant is that aqueous solution of phosphoric acid, so H3PO4. And that equals my Ka. So since this was the first proton that comes off, we're going to use K1. Okay, these really should say Ka1. And that's equal to 7.5 times 10 to the negative 3. So substituting everything in, our Ka is equal to x times x, so that's x squared, over 0.100 minus x, but we're going to again ignore this x because this is a weak acid, and so the amount of hydrogen that dissociates is very small, divided by 0.100, and that equals our Ka. And so you plug all of this in and you get x equals 2.7 times 10 to the negative 2 molar. So that's our x, at least for our first dissociation. Okay, that's all we had to do for the first one. So let's go ahead and draw a line. Now, this has 3 protons to actually donate, so we got rid of one, and so now we're going to see what happens to the next one. So far there's been nothing different. So now that that proton is completely dissociated, we're starting with H2PO4 because we lost a proton, so let's see what happens with the next one. Let's take off another proton. So H2PO4 minus is in equilibrium with H+, loses an H+. We have HPO4 2 minus now. And so now we've dissociated our second proton. So let's take a look at what our concentrations are at this point. So again, you're drawing your ice table. So H2PO4 minus, how much of that are we starting with? Well, it doesn't tell us here. We figured it out here. So at the very end, the H2PO4 that we had was just X. So it was this amount here. So we figured out that we ended with 2.7 times 10 to the negative 2 molar of this stuff, of H2PO4. So that's what I'm starting with here. 2.7 times 10 to the negative 2. And how much H plus are we starting with now? Well, we had some H plus at the end of the last dissociation, so that's also X. So that X, again, is 2.7 times 10 to the negative 2. HPO4 2 minus, well, that's brand new so far. We haven't made any of that. So, 0. And then we just move on like we usually do. So we're going to lose some X amount we don't know. We're going to gain that same X amount there and there. So your ending numbers are 2.7 times 10 to the negative 2 minus X. And then 2.7 times 10 to the negative 2 plus X. And you have your X there. Alright, let's write our second Ka expression. So this actually, I'm going to write a little 1 so we don't get these confused. Ka2 equals, and then we have our products over reactants. So H plus times HPO4 2 minus over a reactant H2PO4 minus. And that's going to equal our Ka2. Our Ka2 is a second proton dissociation here. So we're going to write that down. Equals 6.2 times 10 to the negative 8. So that's our Ka2. So let's go ahead and plug everything in here. Ka2 equals concentration of H plus, that's 2.7 times 10 to the negative 2 plus X. So again, we're going to assume that this X is very, very small because the amount of hydrogen that's going to dissociate here is going to be tiny compared to what we already have. So the concentration of H plus then is just 2.7 times 10 to the negative 2. We'll write the plus X, but then I'm going to show you we're not even going to take it into account. HPO4 2 minus, that's just X. That's a brand new compound that we just formed this time. Okay, over reactants, H2PO4 minus, how much of that do we have? 2.7 times 10 to the negative 2 minus X. And again, that X is tiny, so we are going to disregard it because it's not going to make a difference in our final numbers at all. And so that's going to be equal to Ka2, which we said was 6.2 times 10 to the negative 8. Alright, so when you plug all of this in, you find that your X is equal to 6.2 times 10 to the negative 8. So it's the same as the Ka. Alright. That was our second proton. We still have one more to go. So the last one is right here. It's on HPO4 2 minus. So that's what we're starting with. And it's in equilibrium, and if we tear off that last proton, we're left with just the phosphate ion, PO4 3 minus. Here's our ice table. And then again, we're going to look at our previous table to see what we start with. So I want you to go ahead and pause this video and see if you can figure out this ice table and then come back. Okay, so our HPO4 2 minus was just X. We figured out our X was 6.2 times 10 to the negative 8. So that's how much we're starting with. 6.2 times 10 to the negative 8 moles of that. Okay, our H plus, what was that? 2.7 times 10 to the negative 2 plus X, and we ignored the X, so it's just 2.7 times 10 to the negative 2. Then the phosphate ion, brand new this time. We didn't have it before, so we don't have any of it yet. And then again, just as we have always done, minus X plus X plus X. 6.2 times 10 to the negative 8 minus X. I hope you're seeing a trend here. We're doing basically the same things over and over. We're just tearing off one proton at a time. We'll do our Ka3 equals products over reactants. H plus and phosphate over HPO4 2 minus, and that's going to equal our Ka3. So if we go back in our original problem, it lists our Ka3 as 4.8 times 10 to the negative 13. So that's equal to 4.8 times 10 to the negative 13. So again, I'm just going to plug everything in. The H plus, I'm going to ignore the X, because we're going to assume it's very small on both of these. Alright, so these X's we're going to assume are very small. And that's going to be equal to 4.8 times 10 to the negative 13, just bringing down that Ka3 here. When I plug all this into my calculator, I get X equals 1.1 times 10 to the negative 18. And so that's my X. Alright, so now I've figured out all of these different steps, all these different dissociations, and now the problem is asking me to find the pH and the concentration of all the species there. So let's go ahead and do that. So let's first do the concentration of phosphoric acid. So the concentration of H3PO4. Okay, so H3PO4 is going to be right here, 0.100, so you can't see that, H3PO4, 0.100 minus x. So that equals 0.100 minus x, which plugging in x, we have 0.100 minus, and then our x there is 2.7 times 10 to the negative 2. So our x here for that problem was 2.7 times 10 to the negative 2. Now x goes with this problem. And when you plug that in, you get 0.070 molar. So that's your concentration of phosphoric acid. Let's look now at the next species, H2PO4 minus. So H2PO4 minus at the end here was 2.7 times 10 to the negative 2 minus x. So 2.7 times 10 to the negative 2 minus x minus, let's see, what was our x there? 6.2 times 10 to the negative 8. Now, if you plug that into your calculator, you will see that this x really didn't make a difference at all. And so you still have 2.7 times 10 to the negative 2 molar. This number is just too tiny to even make a dent when we care about sig figs. So 2.7 times 10 to the negative 2 molar. So that's your answer for this one. I'm going to put boxes around these so we can see where we're ending up here. Okay, next species, HPO4 2 minus. So let's find that. HPO4 2 minus is here. And I want you to notice I'm always looking at the most recent HPO4 2 minus. I'm not going to look just at x here. I'm going to look at the most recent ending amount of that, because that's taken everything into account at the end. So that's 6.2 times 10 to the negative 8 minus x times 10 to the negative 8 minus x minus, let's see, what was that x? That was 1.1 times 10 to the negative 18. Really, really tiny. And plugging that in, you'll see that it's still 6.2 times 10 to the negative 8 molar. Okay, last species, just phosphate. And phosphate was just x, so that one's easy. That one's just x. 1.1 times 10 to the negative 18 molar. Okay, next thing we need to find, the concentration of hydrogen ions, so H+. The concentration of H+ at the very, very end here. You're going to want to always pick the one at the very end, but as you'll see, it hasn't really changed. Really, the only the first association determines the H, but you just look at the end. So H+ equals 2.7 times 10 to the negative 2 minus x. And x again is really tiny, so it's not going to do much. It's not going to do anything. 2.7 times 10 to the negative 2 minus 1.1 times 10 to the negative 18, and that's still 2.7 times 10 to the negative 2 molar. And so if you're on a test, you don't have to write this out. If it's super tiny like this, it's not going to make a difference. You won't get marked off if you don't write this part. Then you just go straight to the 2.7 times 10 to the negative 2. So let's calculate the pH then. So the pH equals negative log of the hydrogen ion concentration. So equals negative log of 2.7 times 10 to the negative 2. And that equals 1.62 for our pH. So, one thing that we were going to note there is that the concentration of hydrogen ions only depends on the first dissociation. The rest are negligible. So on this very first dissociation, the number of hydrogen ions that came off there, that 2.7 times 10 to the negative 2 molar, that amount, really persisted, because the next amount of hydrogen ions that came off were negligible. Not very many dissociated in the second dissociation. It was only 6.2 times 10 to the negative 8. That's a really tiny number. And then for the third dissociation, hardly anything came off. I mean, there are 17 zeros in front of this. It's a really small number. So really, only the first dissociation mattered for the pH and for the hydrogen ion concentration. So we're gonna write that down here. So H plus only depends on the first dissociation. The rest are just negligible. So concentration of H plus only depends on the first dissociation. Okay, why is that? Why is K1 so much bigger than K2 or K3? Well, it turns out that, and this is intuitive, as more hydrogen ions are removed, the compound is going to become more negative. So because it's more negative, it's attracting those hydrogen ions to it more strongly. So it's going to be harder to remove positive charge from more negative ions. So as more H plus ions are removed, the compound becomes more negative. It's harder to remove hydrogen ions. From more negative compounds. Because opposites attract, the more negative you have, the more it's going to attract those positive hydrogens, and they're hard to tear off. Alright, I hope that was helpful. That's the end of polyprotic acids, video 432.